So this will be the general concept for Bernoulli's equation. You have your equation down here. And let's just say there's a pipe with water running from the top down to the very bottom. The area of the pipe doesn't change. So the area here, and area down here is going to be constant, doesn't change. So you have your equation here. P is pressure of the water as it goes down, plus the density of the water times by gravity, times by the height, which will change as the water goes down, plus half times the density times by velocity squared of the water is equal to a constant. Density of the water and gravity are also constants. So if pressure, height, or velocity changes, one of them would need to change as well for this to remain true. So let's just say, for example, if the pressure decreases, then velocity may need to increase for this to remain true.
We can then rewrite this equation for the constant of the system. Using the reference points P1 and P2 for our system, we can then further derive Bernoulli's equation to include P1 and P2. And because they're both equal to constant of the system, we can make them equal to each other. And we've set the parameters that V is unchanging, which means we now know that if we are to increase the pressure of the system, then something else in the equation must decrease. And because we know velocity is a constant, it must be the height of the system must decrease if we increase the pressure, and also applies to the left-hand side and vice versa. From equation 1, we have the constant half rho v squared on both sides, so we can then further derive that equation to equation 2, and then we can then make P2 the subject of these equations to come up with equation 3.
These are the applications of Bernoulli's principles.
And these are some examples.
This is an example of a siphon where water has been taken out of it.
And water is moving from a higher potential beaker to a lower potential beaker.
As you can see, the water is being drained and actually going through the tube itself.
And Bernoulli's equation is being used to show how fast the water is actually flowing through the tube.
Another example of Bernoulli's equation is a dam.
Because of all the moving water going through, generating electricity and going through all the pipes.
Bernoulli's equations are used to measure the dimensions of the pipe,
The strength,
the type of material,
or the width.
This all contributes to the flow of water inside the pipes.
Bernoulli's equation affects all fluids.
Because air is a fluid, Bernoulli's equation affects it as well.
This is used in devices to help calculate the cabin pressure of planes.
Bernoulli's equations can also be used to calculate the uplift done on the wing of a plane.
Or how any object moves through fluid like air or water.
Bernoulli's equations plays a massive role in the calculations and the measurements which is used in examples of aerodynamics.
Just like the previous example of the plane, or like downforce on a racing car.
Downforce is created by how fast the car is moving through the fluid itself.
And so as objects speed up, you get greater downforce. Bernoulli's equation has many applications in engineering.
These applications can be done towards different kinds of fluids like air and water.
Using Bernoulli's equation, you can calculate pressure, velocity, the height difference between places from the pressure,
and the rate in which the actual fluid flows through.
And it can be combined with many other aspects of engineering.
This can be used in civil, mechanical, and aeronautical engineering.
So like machines, buildings, or hydraulics.